Nice. Yeah. So welcome everyone. Cozy group tonight. Really cool that you made it here to the AI campus. My name is Alex. I'm a machine learning researcher at Merantix Momentum, and we're a company that does both machine learning consulting and research. And yeah, we host this event called AI Paper Spotlights for a while now, and it's basically here to bring together the community around machine learning research in Berlin. And yeah, it's really a space for you to connect and for you to educate yourself on exciting knowledge and papers. So yeah, I wanted to introduce to you Alma. She's a coworker of mine, and she will be speaking tonight about a recent publication that our team has developed and is presenting very soon at NeurIPS. So that's really, really cool. Our first full NeurIPS paper. And yeah, I'll just briefly introduce Alma to you. So she studied maths in Lund University and the Technical University of Denmark. And afterwards, she's gone on to do a PhD in cognitive neuroscience, also at the Technical University of Denmark. And afterward, she went on to do a postdoc at Potsdam University in the same field. And we're very lucky that we were able to lure Alma into industrial research from her academic background around a year ago, I think. And well, now she's standing here with her first NeurIPS publication, which is very cool. And yeah, I also have some sad news to share, unfortunately. So actually, for me, it's also good news. But I'm gonna leave Merantix Momentum to do a PhD in robotics, but I'll probably stay here in Berlin. And as of now, for the future, Alma will take over the organization of this event. So she'll be your new host, and I'm sure she'll do a superb job at it and host the next events for you. And we have some really exciting stuff in the pipeline. So thanks again, Alma, for taking over. And I think, yeah, without further ado, I'd love to hand over to you. And thank you so much for giving this talk. We're really excited about it. Thank you.
Thank you. Also, big up to Alex for organizing the AI paper spotlights for such a long time and building this great following. It's a really cool event.
Thank you.
So I'm really happy to be speaking here today because actually AI paper spotlights, or paper reading group as it used to be called, was kind of my gateway drug to AI campus and Merantix. I was here last year on a hot summer night. Had some interesting discussions around perceivers, had some cocktails, and then a couple of months later, I started working here, basically. So I'm very happy to be presenting today. Also, on that note, we have an open position in our team right now for a senior machine learning researcher. So if anyone's interested, you could also hit up me or Alex after the talk, and we're happy to tell you more. So yeah, with that, let's go on to the talk. I've tried to make this title a bit provocative. Carve Your Enthusiasm is the title of our paper, but what basically we're trying to do is making so-called interpretable machine learning more interpretable. And Alex already spoiled the good news, which is that it's been accepted as a full-track paper at NeurIPS, our first full-track NeurIPS paper of the team. As you can see, we're quite a big group who have contributed. So I'm very happy to also be representing everyone today, and hopefully I won't do too bad a job at it. So let's dive in. Motivation. Well, I don't think I have to tell you very much about the current trends in machine learning. Let's just say that we have a bunch of very large models doing very complex tasks right now. So these big image and language models can do very impressive things. They're trained on very large data corpora, and they have a crazy amount of free parameters. On the other hand, we have quite a lot of domains in machine learning where we don't have this situation. So we can have quite limited data looking at areas such as healthcare or hiring. We have privacy concerns and we have non-standardized data. We can't just scrape millions of samples from the internet. And also, we might not want these black box solutions, because if we want to give advice towards a diagnosis or towards a hiring decision, we want a model that can explain why it's giving this recommendation. So this brings us to generalized additive models, which you can think of. We can start thinking of a very basic problem. So we have a data set where we want to predict mortality risk from some demographic and clinical variables, so age, blood pressure, so on. And the standard kind of statistics approach would be to use something like logistic regression. So here, basically, we have all of our features, x1 through xk. So that would be like age, blood pressure, so on and so forth. And we basically just fit a regression line to each of these. So like a regression slope coefficient here. And then we can also have an intercept. Then basically we sum these together. We apply a sigmoid function to squash them to between 0 and 1. And then we have our prediction. And so this model is clearly quite interpretable, because we can now like inspect the relationship between each variable and the outcome. So this one would have a strongly positive influence on the prediction and so on. We're not doing so much conventional statistics anymore in logistic regression, because we know that we can basically use more powerful models. So here in the generalized additive model, we basically switch out the regression lines to these just general functions of each feature. And we know from, at least if anyone's taken like a basic machine learning course, we know from the universal approximation theorem, right, that we can basically approximate any function with a deep neural network. So we can now basically throw in a small deep neural network here for each feature transformation instead of the regression line. And now we get a model that can capture much more complex relationships between each feature and the prediction. So that's called a neural additive model. So if we have a look at some examples of why this might be a powerful tool for generating interpretable predictions, we can have a look at these figures from the original NUM paper that came 2 years ago. So here, the color shading is the data density in the training set. And the line here is basically this F1 of X1 and so on. So here we can directly see the relationship between age and mortality risk, and heart rate and mortality risk. And as you can see, in the age variable, we can see that with increasing age, you have increasing mortality risk, which makes sense. We can also see that this risk seems to be a nonlinear function of the age. So that motivates also why not just fitting a regression line would be a good idea. I'll just drink. So with a heart rate, I think we have an even more interesting pattern, because here we see this little strange bump here, just above a heart rate of 160. In general, it would make sense, right, that if you have an abnormally high heart rate, you probably have a higher mortality risk. But this little squiggle here is actually a treatment effect. So around a heart rate of 160, there's usually there's like a treatment protocol that kicks in that basically doctors will start treating this abnormality, thereby decreasing the mortality risk. So of course, if we just threw in a black box model to predict this, it would just predict a lower mortality risk for any new patient that comes in with a heart rate of just above 160. But that's an erroneous prediction, right? Because then you also you have to count in this treatment effect. So basically having this type of transparent model that shows the relationship between every feature in the prediction, clearly it can like expose these treatment effects, confounders, bias, and so on, because we can easily inspect the model. So I hope thereby I have I've made you excited about generalized additive models. So now we can go to the party poopers, which are multicollinearity and concurvity. So going back to some basic stats again, if we have a linear model, so just a regression model again, multicollinearity refers to a correlation between the features. So if we have a little example here, we did a little GIF for you, where basically we vary the correlation between the two features here, x1 and x2, and we try to fit a model predicting this y variable. And you can see when they're decorrelated here on the right, it's easy for the model to find the regression line. But when they become more and more correlated, you see that the uncertainty bands more or less explode. So basically, if we would fit a model multiple times to this highly correlated x1 and x2, we would find different relationships between the features and the prediction each time. So that's a problem for interpretability, right? Because then our interpretation becomes random, more or less, becomes uncertain. So for generalized additive models, the story is a little different because now we have these nonlinear transformations of each feature. So there instead, we can look at the correlation between these non-linearly transformed features in the data, basically. And this is a little difficult to wrap your head around. We have spent quite a lot of time discussing this and trying to wrap our heads around it. So therefore, I'm just gonna try to give some intuition with an example to start with. So in this example here, we have, this is our data. So this is a time series here with some daily and some weekly components. So you can see that there's something that happens every day, but there's also something that happens only Thursday and Friday. So we can fit this as a sum of periodic components. And some components will have a daily seasonality and some will have weekly seasonality. So we can do this with, we've been using this model neural profit that basically has some defaulting to quite a low number of components. So here we just have a few daily components, a few weekly components. So we get something like this that kind of approximates the data, but it doesn't fit super well. On the other hand, if we add a bunch of more periodic terms in this sum, we can get a really good prediction. But now we start to get this confusing mixing of components, right? So in the weekly component, we have a bunch of daily patterns now. And in the daily component, we have a bunch of things that don't seem to really match up to the real observation here. So they seem to actually have some self-canceling features that are really high amplitude. So we can also see here, if we take the correlations between the features, we see here that they have a strong negative correlation. So that indicates that there's some self-canceling behavior happening. On the other hand, if we now try to control for concurvity, and I will tell you how we do that later on, but basically we can keep the many features, but we constrain the model to have low correlation between the transformed features. And this basically gives us the best of two worlds. We have a good prediction, it fits the data really well, and we also have a clearer separation of the weekly and the daily patterns. So basically, in the linear models, to recap, we have a problem of multicollinearity. And you can think of this problem actually as the problem of there being non-trivial zero combinations of the features. So if we can find constants not all zero, such that the features all sum to zero, we can just basically add an arbitrary number of these zero combinations to our model, and we can find an infinite number of equivalent models. The same applies for the generalized additive models, where basically, if we can find a non-trivial zero combination of the transformed features, we can do the same. So that's where the concurvity regularizer comes in. So we've already defined our concurvity now as there existing a non-trivial zero combination of the transformed features. So in order to exclude this situation, we found this insight that basically if we can make sure that each pair of transformed features are uncorrelated, the concurvity is impossible. And we have a proof of this in the paper. I'm not going to go through it now because I think it will be a little maths heavy, but it's quite easy to show. So basically, what we want to do then is we want to optimize our model over this domain where each of these transformed features are now perpendicular to one another. But we didn't find a way to basically analytically directly optimize over this domain. So instead, we just throw in the classical machine learning method of regularization. And I think basically this is a very simple approach. I think familiar to most people who have done some machine learning. Basically, while we minimize our loss function, which is this L here, we simultaneously optimize for our regularizer. And here our regularizer is basically the average absolute correlation between each feature pair, normalized by the number of feature pairs. So yeah, we can just throw this into any favorite framework for automatic differentiation and just plug it in and optimize our model. And that's what we did with a bunch of data sets. So we have run experiments on 6 tabular data sets, Boston housing and California housing, which are both regression tasks where basically you want to predict the house price from a bunch of features. We have adult, where you want to predict salaries of people in the US, actually just a binary prediction whether or not it exceeds a threshold. And then we have these 3 medical data sets, MIMIC2, MIMIC3, and support. So the first thing we wanted to know was how can we find a good trade-off between these 2 objectives? So we simultaneously optimize for a good model prediction, so minimizing the loss function, but we also want to decrease concurvity at the same time. So we can do that by basically varying this lambda, which is, if I go back again, sorry. So the lambda here will be basically the scaling of the regularization term, basically determining how much we prioritize the regularization versus how much we want to minimize the loss function. So going back, you can see that with a low value of lambda, so with a weak regularization, we have quite a high observed concurvity in the validation set. Whereas if we increase regularization, this concurvity drops, and then it kind of, we start to get a large increase in the error function. So this is a trade-off. We won't be able to constrain the model while preserving the exact same prediction quality. So this is kind of an empirical choice you have to make. In some instances, it's quite easy to identify, for example, here, it's quite easy to identify what would be a good setting for the regularization term. That's a long word. But yeah, so this has to be basically determined on a data set by data set basis. But what we can see is that in many cases, we can definitely reduce the concurvity quite a lot without severely impacting the model fit. So if we go a little deeper now on California housing, because these trade-off curves, they still don't really tell us much about the interpretability, right? And this is all about increasing interpretability. So if we take a deep dive into California housing, we can first have a look at what do these features actually look like in the input space. So we can see that here we have, I think, 8 features, and some of them, there's a cluster here that are really strongly correlated. So this is a correlation matrix. And if we look at the correlations between the transform features, when we fit our neural additive model, we see that some of these correlations carry over. For instance, here we get quite strong negative correlations. This correlation here persists, so there's clearly concurvity in the model. When we apply regularization, this correlation disappears. And if we look at what that means now for the model's interpretation, or our interpretations of the relationship the model finds, we can look at the feature importance derived from each model. So here we've ran 60 random initializations of each condition. And the blue dots here are the runs for the unregularized model, and the orange ones are for the regularized model. And so what you can see is that the blue, the unregularized model clearly has a lot larger larger importances as estimated by the model, and also a much larger variance between the initialization. So you can see that these importances are much less consistent. between the runs, which is a problem, right? Because we want as little randomness in our interpretations as possible. And we also see that some of these features, many of them have much lower importances estimated in the regularized model, which seems to indicate that some of these features are becoming pruned. We also see that we do get a little higher error estimated by in the predictions estimated by the regularized model. I would say it's around 10% error sacrifice that we make here. But what's interesting then is when we look a little deeper into what do these importances actually mean, we can see that here, if we look at the median income, which is a feature that's actually not correlated with any other feature very strongly, it's basically unaffected by our regularizer. So here, the blue and the orange are on top of one another. And here for baseline, we've added PyGAM, which is an older generation of generalized additive model that's based on splines. And so basically all these three models are in quite good agreement with one another. So I think that's good. We show that our regularizer doesn't do crazy things. On the other hand, if we look at this cluster of more strongly correlated features like population and households, we see that the blue lines here, they don't agree very well with one another. You can see that they spread out quite a lot. Here, each individual line is one model run, basically. Whereas the orange one is basically pruning away this feature. And the same goes for population. So these two features seem to have been sort of canceling each other out. In the unregularized case, it's a positive correlation in the input space that goes to a negative correlation in the transform space, basically indicating self-cancellation. And this is removed by our model. You can also see that PyGAM, our baseline model in these instances, kind of explodes. So here it's completely uncertain of how to estimate. Basically, this green part is the confidence band, and that's filling the whole the whole plot. And here it's also very wide. So we remove quite a lot of uncertainty in these shape functions by applying the regularizer. So going towards the conclusion, I hope that I've convinced you that interpretable models like these generalized additive models are useful in many real-world applications. So like, let's not only focus on the huge, impressive LLMs, but also think of these smaller modular models. Also, interpretability relies on low uncertainty, clearly separated individual feature contributions. So we don't want an exploding uncertainty when we want to determine the relationship between a feature and a prediction. We also don't want to have to cross-reference features if they have basically opposing contributions, and we have to subtract one from the other to get the actual contribution. So concurvity impairs interpretability exactly by this, by allowing that features are mixed together and basically decreasing the certainty. We saw in the case study that self-cancellation disappeared with our concurvity regularizer, which is really nice. And so this brings me to the title of the paper, Curb Your Enthusiasm for Generalized Additive Models. You should watch out for concurvity before you draw conclusions. So you actually get true interpretations of your results. Thanks. Oops. These are additional results.
Great. Thanks so much, Alma. So such a pleasure to see that presentation. Great. Do you have any questions from the audience? Yeah.
Thank you. It will take time to understand this also. I will give some naive question. You said we can vary lambda depends on our choice. How much this affects interpretability? Because you said if two features are correlated, the problem is that you can get several solutions. Isn't it the same case if you can vary lambda?
Yeah. So I think this is a really good question, and it's something that we've been grappling with as well. Because of course, like in the wild, in nature, there are true correlations between things. Things do correlate. And basically how much you want to restrict your model, I think depends quite a lot on the application. And so we see this as part of kind of an iterative process where you basically develop your model together with domain experts, or kind of communicate with domain experts. So for example, in the first example that I showed of these shape functions where you have the heart rate basically decreasing mortality risk after some threshold. These are things that we as just generalists cannot really interpret well, right? So these models should be developed ideally together with domain experts. And also I think there might be different trade-offs to be made in different practical applications. So I think in general, in the interpretable machine learning field, there are not so many straightforward metrics as of now. And so it's more of kind of a practical from case-to-case approach at this point.
Thank you.
Yep.
Thank you very much. It was an interesting topic. My question is that have you tried it over synthetic data that you generated, so you know all the causal relationship between the data, so we can?
Yes. So that was kind of the spoiler. Let's see. My spoiler that I did here. So we did a bunch of toy examples. This is the easiest one, where basically we have two variables, x1 and x2. We have y that depends only on x1. And we vary the correlation. So we have a completely uncorrelated case, strongly but not perfectly, and then perfectly correlated case. Let's see, now I've actually flipped the legends here, so this should be uncorrelated, sorry. So in the uncorrelated case, we find our model can very easily find the true relationship, which is that x1 is perfectly correlated with y, and x2 is not. So here it finds the relationship both with and without regularization. In the strongly correlated case, we see that basically it estimates that both x1 and x2 correlate perfectly with y, which is wrong. Whereas here in the correlated case, we get this kind of quadrant of a circle, I would say, where most of our points actually end up towards the right relationship, that x1 correlates perfectly with y, whereas x2 does not. And then in the perfectly correlated case, of course, there's no possibility of differentiating between the two, and then the balance is more even.
Okay, that is wonderful. Thank you.
Any other questions? Yeah. Yeah, so people in the audience, like online, won't hear it otherwise. Yeah.
Very loud voice. Thank you so much. As a complete non-AI person, don't understand machine learning or statistics whatsoever. I'm very curious in terms of use cases, practical applications. I can see how this makes sense as something to use in research. Outside of that, could you just paint some pictures for me and maybe anyone else like me who decided to drop by?
Yeah, I think we already have some neural additive models in production at our company that are basically running for client projects. So whenever you basically have a data set with columns, so rather than an image, which is like a 2D structure, or a text, which is sequential, if you have a tabular data set where basically the data is arranged in columns, you can throw this class of models onto it. And then you can basically get out these feature functions and everything. But then basically controlling for the concurvity, I think especially becomes important when you have strongly correlated features, such as in the California housing example. And there basically we could make the predictions more stable, and especially the interpretation more consistent. Sure.
So in terms of the kind of conclusion of saying that these GAMs can be useful, not just super large models as well, can you give a sense of how reasonable it would be for a standard like lab or researcher to implement these kinds of more limited tailored models as opposed to the large ones, the kind of compute needed, etc.?
Yeah, so what's nice with these, I think we ran all of these experiments locally on a MacBook. So that's pretty nice. It depends on, of course, how many features you have and how, like, the hyperparameters. So we did some hyperparameter optimization. And so the depth of the feature networks and also the width is a bit different for each data set. But yeah, we basically didn't use any fancy compute for this. So I think it's quite nice.
Mm-hmm.
Okay, if I tomorrow would like to apply this model, where should I put this in my code? Like, I have optimizer, and should then I add regularization as restriction, or it was a solution for the optimizer that you have shown?
Yeah, so we have a GitHub repo where you can just clone it and run it. We apply the regularizer after we do a warm-up of 5% of the optimization steps we do without the regularizer, for it to start to kind of hone in on the right region, and then we start regularizing basically until the end at each iteration. What's good as a practical note is that it's good to have a rather big batch size, because the value of the regularizer will depend on the average correlation of the features within the batch, basically. So if you have a large variability in that due to small batch size, then it might jump around a little bit.
Thank you.
I have a question. So for the California housing dataset, we saw that there was a decrease in model performance once we add the regularizer. Did you see some case where the performance maybe even improved or stayed the same?
Basically, no. We can go back to these trade-off curves. So you can see here that there's basically always a little bit of a cost. Here in Boston housing, the cost is almost zero, right? But usually we pay some cost, and I think it would be interesting to do a follow-up analysis of why some are more costly than others. I think it might relate to the feature correlations inside of the data sets, and possibly also interaction terms like first order interactions. So we didn't fit any interaction terms at all. Might depend on that also.
Cool, thank you. Any more questions from the audience? Yes.
Hello, thank you for talk. It was pretty understandable. I like it. But on the next two slides, there are 3 plots. Actually, I haven't got what does they mean.
This one?
Yes, these 3 ones. Like, what happens there?
Yeah. So basically, these are the shape functions again. So this is the relationship between each single feature. So here is, I think, the number of households in a neighborhood, something like that, and basically how much they contribute to the housing price prediction in unit of $100K here. So here, basically, we see that this feature, when we regularize the model, this feature is deemed unimportant, that it doesn't influence the price actually. And the same for population. Whereas if we have the unregularized, which is the blue one here, we see that the number of households have a positive influence on the price, whereas the population has a negative influence on the price. And this is a little funny because they're so strongly correlated, right? That it's not clear why one would be positive and one would be so strongly negative. And this is basically the effect that regularization removes.
Have I got it correctly? It totally removes contribution of households to the price?
Yeah.
Is it kind of true? Like, that doesn't sound logical, do you know?
So yeah, this is always the question, right? What we can see if we look at these importances is that households here is almost zero. So some features basically get deemed unimportant, whereas, for instance, ocean proximity seems to be more important. So yeah, it's hard to, of course, assess what is true, what is actually true. What we can see is that it's more, it's less random, so it's more consistent over random initializations. And the prediction is prediction quality is similar, but we get more consistent predictions. So I think what is the actual truth behind the data is still hard to get at. But we've tried to make this argument that basically the predictions are more consistent. It removes a bit of clearly kind of noisy squiggles in the shape functions. I also have more examples we can look at afterwards if you want. So we think that this improves the consistency of the model because it at least doesn't introduce false effects, basically.
So these 3 plots actually to show that regularization works. More about this. So thank you.
Thanks.
Okay.
Yeah, thank you for the great talk. I was asking myself if you do the pairwise, I just call it orthogonalization, so ensure independence between the features. does the order of how the features are sorted, or which pairs you orthogonalize first, does this play a role there?
No, because basically we do them all at the same time. So here you see basically that we take this full sum over all pairs.
Yeah.
And so we calculate this full term before regularizing, basically.
So you optimize for all at once?
Yeah.
Okay, thank you.
Thank you so much, Alma. Actually, I have one final question to wrap it up. It's very high level. So this has been submitted at probably the most prestigious machine learning conference. Can you talk a little bit about the process of like how it came about, that we even wrote this paper, and then how like the review process felt like, and whether you're excited to travel to NeurIPS?
I'm not excited to travel to New Orleans from Berlin in December. Why would I be? Yeah, of course I'm excited. This is actually quite a long process. So I think it started already at the Merantics Research Day. If I remember correctly, that was in January or February. And we had a keynote presentation on neural additive models because it's something that we've been focusing quite a lot on. And then there was a question from the audience. Well, what happens if they just start to kind of get self-canceling behaviors in the shape function? So you could just basically fit two periodic functions that will cancel each other out, right? And then this, I think, prompted Julian to start thinking about this. And basically, this project kind of ramped up over the spring. So I think that was really cool also to see how this kind of event can spur some new questions and insights, and then actually a paper. Yeah, so we submitted it in mid-May. And then I don't know if anyone has experience with this, but NeurIPS has a really, really thorough review process where basically we had 4 different reviewers, all giving scores and remarks. There's an open, basically 1 week period where you can interact with the reviewers and write messages and try to convince them that your paper is worth publishing. So we had like 1 week of running a lot of additional experiments, trying out basically everything that the reviewers suggested to get them to bump up the scores. And we were just on the threshold, and then we got accepted. So very happy about that. We just submitted, I think 2 weeks ago, the final camera ready version, where we had to deliver on all of our promises, but it worked out. So very happy about that. And actually, with the team, we now have 4 papers to present at NeurIPS, 3 workshop papers, and this full track paper. So it's going to be really fun.
Awesome. Yeah, huge achievement by the team. Really, really proud. Cool. So let's wrap it up. Awesome that you have come here tonight and spent the evening with us. And please stick around. We have a few more alcohol-free beers and beverages here. So talk to each other, and I'll put on some music, and see you next time, hopefully. Bye.